we are Group 29 and we're here to present our findings in steering vision language action models. In robotics right now, many researchers are creating vision language action models or VLAs. The image on the screen shows an example of a VLA, which primarily consists of a large language model in Llama, but it is conditioned on images in addition to text and produces actions as tokens. These VLA models are very powerful because they utilize really smart LLMs and image encoders to reason about actions that can then generalize to many other tasks. For example, these VLAs can fold and hang a tablecloth, and this is just one among many other tasks that it can do.
Using language as its reasoning backbone, these VLA models open up a very interesting question to ask, which is how do the language embeddings in the VLA correlate with the action it produces? To answer this question, we used a method from Berhayan, Kylene, Stocking et al., which is to probe into what the model is thinking by looking at neurons in the transformer's linear layer. Each neuron in the transformer's linear layer multiplies a column of weights. This column of weights has the same dimension of the embedding space, so we can then decode that embedding to get the tokens it corresponds to. With this method, we effectively have a neuron that corresponds to interpretable concepts. We can then artificially amplify the neuron corresponding to the desired concepts to potentially modify the behavior of the VLA. We build upon prior research through a novel contribution of applying this method to a smaller, easier to run open source model called Small VLA.
Our first findings was that these semantic concepts aren't uniformly distributed across the layers. They are concentrated in the middle to late layers. The earlier layers showed strings of undecipherable characters, while the mid to later layers had complete words with semantic coherence. For example, in layer 26, we found a specific neuron with a common semantic theme of fast, that is, fast, quick, swift, rapid. This is the speed dial. In our amplification experiments, we found many neurons associated with semantic embeddings like fast, slow, high, low, and amplified them with a sweep of values from the range of 2 to 50. Then we measured the characteristics of the robot in 10 rollouts for the condition with an amplified semantic value vector, random value vector, the semantic characteristic in the prompt, and the basic prompt. We measured the performance of each condition through average speed and height. Looking specifically at the fast semantic experiment as an example, we found that the semantic amplification exceeded in speed compared to the random amplification. But as you can see in the table, it was only a nudge, not a separation. Differences are within a standard deviation. We also found that the modified prompt beats neuron steering. Qualitatively, you can also see it visually that there isn't much of a difference. Our interpretation of the failure of the experiment would be that small VLA is a small 500 million parameter model, so neurons could have many meanings. This could weaken the connection of fast to fast moving robots. Previous research of the same kind with good steering used large VLAs of 7 billion parameters. We believe that having small models causes less semantics, which makes the model less capable in steering. Next steps would be to confirm the polysemantic hypothesis through more experiments, such as seeing if the slow and fast value vectors are orthogonal. Thank you.